So today what we're going to talk about is integrals involving trig functions, and particularly we're going to be focused on integrals that involve sines and cosines. And in fact, let me just make sure that I have this little set of notes where I can see them. There we go. Sort of. There we go. Okay. So we're going to focus on these integrals involving sines and cosines. Now, the first thing to observe is that if I have something that's just, the integral of sine theta d theta, well, of course, this is just negative cosine theta plus some constant. And if I have the integral of cosine theta d theta, this is, of course, just sine theta plus a constant. So those are fairly basic. And we know these because we can easily just see this from looking at the table of derivatives. We just read the table in reverse, and this is what we get. Now, what we're usually interested in, though, it's not quite something as simple as this. It's when we have things involving products of multiple trig functions. So, for example, let's suppose that I wanted to do the integral of sine theta times cosine theta d theta. Well, one way that I could do this is actually I can use a substitution. So what I can do is I can say, let u be equal to sine theta. Then du is equal to cosine theta d theta. And that means that what I really have is the integral of u du, which is going to be equal to u squared over 2 plus a constant. So that is going to be equal to 1/2 sine squared theta plus a constant of integration. And there we go. This is a rather nice little technique that we came up with here. It's a fairly straightforward substitution, Now notice, I could have done the substitution in a slightly different way. I could have done a substitution using u equals cosine theta. We would have picked up some negatives and things, but it really would have come out to be the same thing in the end. Because remember, and this is going to be key, not just for this, but in other examples here, remember that there are a lot of identities that hold between the different trig functions. So sometimes you will get two answers that are equal, but they don't look the same. It's just that they're equal after you apply the correct trig identities. Now, this same kind of trick is going to work just fine anytime you have a product involving sines and cosines when you have just one of them, and then everything else is the other. So examples of this would be something like, let's suppose that I have the integral of sine to the 7th theta cosine theta d theta. Well, once again, what I can do is I can take u to be equal to the sine of theta. Du is going to be cosine theta d theta, and therefore this integral is going to be the integral of u to the 7th du. That's going to become 1/8 u to the 8th plus a constant. And then this is going to become 1/8 sine to the 8th theta plus a constant. And this also works if the roles are reversed here. So this would also work if I wrote something like this. So let's suppose that I have, let's do something slightly smaller, but we'll still make it relatively complicated. Let's suppose that I have sine theta cosine squared theta d theta. Well, for this one, I'm going to need to take my u to be equal to cosine theta, and then my du will be negative sine theta d theta. So this integral is actually going to be the integral of negative u squared du, which becomes negative, I'm losing things here, negative u cubed over 3 plus a constant, so this becomes negative 1/3 cosine cubed theta plus a constant. So you can see this worked out the same way. It's just that I'm using the opposite kind of substitution. I took my u to be cosine theta instead. Okay, so this actually, like this technique will generalize to a whole family of integrals. Anything that involves a power of sine with one cosine, or anything that involves a power of cosine with one sine, I can use this trick and I'm all set. But what if it's not quite that simple? What if we have something a bit more complicated? For instance, what if instead of that nice simple little thing that I had there, what if I had the integral of sine cubed theta cosine squared theta d theta? Well, now things are not quite so simple. Now we're going to need to be a lot more careful about this sort of thing. But there's still a trick that we can do, and it comes back to the fact that there are trig identities. What I'm going to do is, if we can, we would like to peel off a single sine theta or a single cosine theta. And if one of them has an odd power, that is the one you want to peel off. And you'll see why I'm doing it this way in a moment. I'm going to rewrite this as the integral of sine theta times sine squared theta cosine squared theta d theta. The reason I'm going to do this is because as long as this sine squared, as long as this involves an even power, I can rewrite this entirely in terms of cosines. Why? Because sine squared theta is equal to 1 minus cosine squared theta. That identity now allows me to rewrite this as the integral of sine theta times 1 minus cosine squared theta d theta. Excuse me. So now what can I do? Well, now I can rewrite this as the integral of sine theta cosine squared theta minus the integral of sine theta cosine to the fourth theta d theta. Now, what I want you guys to do is pause this video for a minute and see if you can work out each of these integrals from the stuff that we just said. You can do a similar u substitution on these as we've been doing up to this point. So take a minute and try to practice this yourselves. All right, so what were you able to do? For both of these, the substitution that I make is going to be the same. I'm going to make the substitution u equals cosine theta, du is negative sine theta d theta. So these integrals are going to become the integral of negative u squared du minus, actually plus, because the two negatives cancel, the integral of u to the fourth du. This is going to become negative 1/3 u cubed plus 1/5 u to the fifth plus a constant. This becomes negative 1/3 cosine cubed theta plus 1/5 cosine to the fifth theta plus a constant k. And give me 1 second here. All right, so returning to this, so we've got to this point, we figured out how to do this, and you'll notice this exact same trick will work anytime that I have an odd power of sine. So what we can actually do is the same trick is going to work anytime that I have something like the integral of sine to the 2m plus 1 theta cosine to the n theta d theta. This trick will always work because I can always rewrite this as the integral of sine theta sine to the 2m theta cosine to the n theta d theta. And I can rewrite this as the integral of sine theta 1 minus cosine squared theta raised to the nth power cosine to the n theta d theta. Now, I then have to expand out this binomial expression here, and it's going to get ugly and end up involving a lot of terms, but we can do it. Okay, so you can do this as long as you have an odd power of sine. The same is actually true if we have an odd power of cosine, except we do the opposite kind of thing. So let's take a look at that sort of scenario. Let's suppose that I had the integral of, say, sine squared, I cannot write today, sine squared theta, let's say cosine to the third theta d theta. Or, yeah, let's just go with this, because it'll illustrate what I'm talking about. I can use the same kind of trick, except this time I can't do exactly the same thing because I can't peel off a single sine. The problem is that if I do that, I'm left with an odd power of sine, and I can't use the identity anymore, the Pythagorean identity. But what I can do is I can peel off a cosine. That leaves me with sine squared, cosine squared, and a final cosine theta. And then what I can do is I can use the fact that cosine squared theta is 1 minus sine squared theta. So this is actually the integral of sine squared theta times 1 minus sine squared theta cosine theta d theta. And we actually don't even need to expand this whole thing out like we did in the first time. I can actually just directly do a u substitution and say, let u be equal to the sine of theta. Du is cosine theta. So this integral is the integral of u squared times 1 minus u squared du. And of course, that is actually the integral of u squared minus u to the fourth du. And if we come back to the top, make sure you have this written down already. This is going to become u cubed over 3 minus u to the fifth over 5 plus a constant. Then I just have to replace my u's with sine theta. So sine cubed theta over 3 minus sine to the fifth theta over 5 plus a constant. And once again, this trick will always work as long as I have an odd power of cosine. So anytime that you see something that looks like the integral of sine to the n theta cosine to the 2m plus 1 theta d theta. Notice, by the way, that 2 times an integer plus 1 is always odd. So this is just a way of writing out a general odd number. Well, you can rewrite this as the integral of sine to the n theta cosine to the 2m theta cosine theta d theta. That's a du, d theta. And that is going to give me the integral of sine to the n theta times 1 minus cos squared theta to the nth power cosine theta d theta. And then you do a u substitution. U equals, sorry, this should be 1 minus sine squared theta. And then you do u equals sine theta as your substitution. This will always work. It may give you sort of a mess, but it will always work. So multiplying these products of sine theta and cosine theta is actually not too bad as long as one of the powers is odd. You take whichever one is odd, you peel that one off, and you use the other one as your u substitution. So if the cosine has the odd power, your substitution will be u equals sine theta. If the sine has the odd power, your substitution will be u equals cos theta. If you are dealing with a situation where both are odd, then it's your choice. Do whichever one you want. I usually prefer to do the substitution u equals sine theta because that way I don't need to worry about the differential picking up a negative sign, but whatever you do, you can do it either way, and the results will be equal, although they may not initially look exactly the same. You may have to do some kind of trig identities to get them to be the same. So as long as one of our powers of the sine or the cosine is odd, we're all set. Now, the problem comes in if these things are even. And in order to understand what to do if they're an even power, I want to take a look at what happens if we just have sine or cosine by themselves, first of all. So what if I have something like, let's make this easy and do the integral of cosine squared theta d theta, just to do something that's relatively simple and straightforward to start. Well, what is this exactly? There's a couple of different ways that I could probably do this. One thing that I could try to do, I guess, is I could kind of try to say, well, this is actually the integral of cosine theta d theta. So I could try doing an integration by parts, and I could say, let's let u be equal to cosine theta. Then du is going to be equal to minus sine theta d theta. dv is cosine theta. V is going to be equal to sine theta. Now, the problem is that when you put this together, it just turns it into a problem involving sine squareds, and you don't really get anywhere. In fact, this is the example that I sort of started into last week, and then said, wait a second, that's not the example I want to do. We're going to save that for this week. Now, this technique doesn't really end up helping you out much. Here's what you can do in order to make this work and not have to worry about this sort of thing. Instead of thinking about integration by parts, which is maybe where your mind would normally go, it's certainly where my mind normally goes, we instead go back and think about the trig identities. Can anybody think of a trig identity here that involves a cosine squared? I'm going to give you a minute to think about that. Well, the answer is cosine squared theta is actually equal to 1 let me make sure I write this correctly. 1/2 times 1 plus the cosine of 2 theta. So, by using this identity, I've managed to get rid of the squaring. Now, this is something that I can integrate, because this is going to be 1/2 theta plus 1/2 sine of 2 theta plus a constant, because I can integrate each of these terms separately. And to do this second one, just use a u substitution, u equals 2 theta. It's a very short u substitution there, and it gives you this answer. So we can now deal with this as long as we are doing, we take the cosine squared and we split it into 1 plus cosine 2 theta with a factor of 1/2 on the front, and then we're able to do this integral. Now, I want to show you the same thing is going to be true if I have a higher power of cosine that is even. So what if I had something that looks like the integral of cos to the 4th theta d theta? Well, this time what I'm going to do is I'm going to say this is the same as the integral of cos squared theta squared. So that is the same as the integral of 1/2 times 1 plus cosine 2 theta squared d theta. Okay, that looks like it's not really going so well so far, but I mean, we're getting somewhere. It's just kind of starting to turn into a tad bit of a mess, let's say. This is going to become the integral of 1/4 times 1 plus 2 cos 2 theta plus cosine squared 2 theta d theta. And we are actually all set here. We're really fine, except that we have this cosine squared 2 theta. But I can play the same trick again. And I can say cosine squared 2 theta, this is actually going to equal 1/2 times 1 plus the cosine of 4 theta. So I can take this integral and I can rewrite it as the integral of 1/4 times 1 plus 2 cosine 2 theta plus 1/2 plus 1/2 cosine 4 theta d theta. And now we have everything down to where we have at most one cosine in each of these. We can do each of these pieces. In fact, we can simplify things still further because this is 1 plus 1/2. It picks up 3/2, and then we just do each of these pieces. Okay, so I'm going to leave that as a little exercise for you guys to think about because hopefully at this point you know how to do these integrals. They're all simple U substitutions. What if we were dealing with powers of sine? Well, let me pose this to you as a challenge question. Can you think of a similar way to integrate the sine squared theta d theta? Well, the answer is there's another similar identity. We can rewrite this as the integral of 1/2 times 1 minus cosine 2 theta d theta. And now this is actually quite straightforward to do. This is going to become theta over 2 minus 1/2 cosine 2 theta plus a constant. And there we go. In fact, exactly the same sorts of thing are going to apply to higher even powers of sine as well. So what we can do is we can always just keep on expanding, kind of like in the previous example. We just iteratively keep on going. So if I had sine to the 4th, I can think of that as sine squared raised to the squared. I break up the sine squared, square that, and then I just keep on going, continuing to simplify it until I get down to something that I can actually handle. And this is exactly the same technique as we can use if we have the integral of an even power of sine with an even power of cosine. So if I have something like the integral of sine squared theta cosine squared theta d theta, the way that I can do this is I can start by expressing everything in terms of sines or everything in terms of cosines. So I'm going to do cosines. I'm going to do, this is the same as the integral of 1 minus cosine squared theta times cosine squared theta d theta. This becomes the integral of cosine squared theta minus cosine to the 4th theta. So from this, we see that we actually turn this into a bunch of integrals of even powers of cosine. What can we do with each of these? Well, we can break these apart by using the trig identities, break it down into simpler pieces. This may require us to keep on going for quite a ways. You know, it's not necessarily going to be a short, simple process here, but we can keep on going at this point because we know how to do these integrals. And this is going to be true whenever we have even powers of sines and cosines. So if you have something that looks like the integral of sine to the 2m theta cosine to the 2n theta d theta, what you are going to do is you can just rewrite everything, use the fact that, sine squared theta is equal to 1 minus cosine squared theta, plug that in here and write this as the integral of 1 minus cosine squared theta to the m cosine to the 2n theta d theta, and see what you can do from that point on to simplify this by dealing with the even powers of cosine. Because when you expand this out, what you will end up with is a bunch of stuff, all of which is an even power of cosine. And then you can apply the identity for cosine squared to get that to be simpler. And you keep on working that way until you get down to the point where you have integrals that you can do. Now, I will warn you, if these are large powers, this is going to end up taking quite a while. But it is possible. Give me just a second to... All right. So that takes care of sort of a bunch of the cases that we can see with sines and cosines. And sometimes as you mess around with them, you may find that other trig identities may help you out as well. So a good idea is, as you're doing these integrals with trig functions, always keep the trig identities in the back of your mind. In fact, if you have a nice little listing of the trig identities with you, it won't hurt. Now, I do want to mention another sort of thing that we can see. What if we need to do a product where, because this can come up as well, and it can even come up in some of the examples that we've been doing, depending on how things simplify out. What if we have to do an integral of something that involves trig functions with different periods? Because everything we've done so far kind of depends upon the periods of the functions involved being the same. Well, what if I wanted to do an integral that looks something like sine of mx times sine of nx dx? What could I do here? Or maybe I have another combination. Maybe it's cosines here. Maybe one's a sine, one's a cosine. The answer is we can use the following identities, which you may remember. The sine of alpha times the sine of beta. This actually can be expressed as 1/2 times the sine of alpha minus beta plus the sine of alpha plus beta. Or I'm sorry, I'm looking at the wrong thing here. Minus the sine of minus the cosine of alpha plus beta. You can tell that I've used these trig identities very frequently because I just managed. Well, really what happened is I was checking my notes and I looked at the wrong line and I confused myself. But yeah, sine alpha, sine beta, this is 1/2. I'm sorry. Let me start this over again because this is completely wrong because I was looking at the wrong line. Let me write down the three identities the same way I had them in my notes. That way I don't have any confusion here. Sine alpha cosine beta is the one that I just wrote down. So this is 1/2 times the sine of alpha minus beta, making sure I really do have this correct, plus the sine of alpha plus beta. There we go. Okay, that is actually correct here. Then we have sine of alpha sine beta. This also has a factor of 1/2. This time we have cosine alpha minus beta. And then we have minus cosine alpha plus beta. And the last one that we have is cosine alpha cosine beta. This one is going to become a 1/2. And then we have the cosine of their difference, so cosine alpha minus beta. And then we have plus cosine alpha plus beta. There we go. Finally, I have these down in the correct order. Now, which of them is going to help us out up here? Well, up here, the one that we're going to use is the one involving two different sine functions, of course. And so we're going to use this second line. So let me leave that up here. I'm going to erase these others that we don't need for the moment and just leave you with this one. This is going to be, therefore, the integral of, now in this case, this is my alpha, and this is my beta. So we're going to do the integral of 1/2 cosine of, let's see, alpha minus beta, so that's going to be m minus n times x, and then we're going to have minus cosine of m plus n times x. and then we're going to have dx. So all I've done is I've used this trig identity to rewrite this integral. Now, I'm going to get rid of the trig identity for the moment and just finish this out. Well, what this comes out to be is assuming that m and n are not equal, and assuming that, because the problem that we might run into here is maybe one of these is just 0, and maybe like the other one isn't 0 or whatever, but the thing is one of them could have come out to be 0, in which case these just give me 1. But otherwise, I just do both of these by a u substitution, and I would end up with 1/2 times the quantity 1 over m minus n sine m minus n times x minus 1 over m plus n sine of m plus n times x plus a constant. And there we go. Similar kind of thing is going to happen, like I said, if one of these is a cosine or if both of them are a cosine. So in those cases, you have to use one of the other trig identities, but it is the same procedure. You rewrite everything in terms of separate cosines. This will come up, by the way, as you deal with things involving, say, even powers of cosine or even powers of sine, because if they're large enough, then the resulting product that you break it into is going to involve products of cosines that don't all have the same period, and therefore you're going to need to do an integral like this, but involving the cosines. So these problems are typically fairly challenging, and the reason they're challenging is simply because they are so involved. There's so many things you have to remember. But you really just have to keep on thinking, how do I break this up into a simpler problem? What identities can I use that will simplify things? And if you do that, then you will kind of see how to get to where you're going. And I'm going to post this week a bunch of additional examples for you guys to look at, because I think seeing some written examples that are carefully written out as references for you, those can be really useful. So I'm going to post some links to that in the reading section for this week. Before we move on to the next topic, which is going to involve doing these same kinds of things, but for tangents and secants, and then of course cotangents and cosecants end up working out similarly to the tangent secant case, I do want to mention an interesting consequence of this. And the consequence of this that I want to notice here is, let's suppose that we wanted to actually do the integral here from 0 up to 2 pi. So what if I did a definite integral here? Well, this would be a definite integral from 0 up to 2 pi still. And then this would be evaluated from 0 to 2 pi. This is assuming that m minus n is not equal to 0 and m plus n is not equal to 0. But when I do this evaluation, sine of 0 and sine of any multiple of 2 pi is just 0. So this comes out to be 0 as long as neither of these conditions is satisfied. That's really interesting because it tells us that the integral of this product over a period of 2 pi is 0 if m and n are positive numbers and are not equal to each other. On the other hand, if m equals n, why did I erase that? I didn't really want to erase that. If, let's say, m is equal to n, then what we really have is the integral from 0 up to 2 pi, 1/2, and then we're going to have the cosine of 0 minus the cosine of 2mx dx, and this is really just 1. So this is going to end up being the integral of 1/2 from 0 to 2 pi is just going to be pi, and then this integral is still going to come out to be 0 just like we had before. So this integral comes out to be pi. And this is a very interesting thing. You can get a similar kind of result if m is equal to negative n, by the way. You just get the opposite sign coming out, because then this is the one that is cosine of 0, and this is the one that integrates to 0. So what we see is that this integral is going to be 0 unless these are equal or the same but with opposite signs. And if they are the same but with opposite signs, then, well, actually, if they're the same but with opposite signs, we can immediately see that we would get negative pi, because if these had opposite signs, if we had the integral of sine mx sine negative mx, sine is an odd function, so this is actually negative integral from 0 to 2 pi of sine squared mx dx. So this would come out to be negative pi. This actually leads to a really important thing in mathematics. There's a branch of mathematics known as Fourier analysis. And what it amounts to, and we'll talk more about this sort of thing later on, but it amounts to the fact that any periodic function can be expressed as a limit of some kind of sum of sines and cosines. And when you do that, the fact that this works so nicely comes out because of the fact that these integrals are all 0 unless these periods are the same. So Fourier analysis, what Fourier analysis actually does for you is it breaks up a periodic signal into its component frequencies. So in other words, it allows you to analyze the frequencies that go into the signal. Now, the interesting thing is that all signals, no matter how ugly they look, can be broken up this way and analyzed in terms of their frequencies. And it all comes down to being able to do these kinds of trig integrals. Okay, so like I said, I'm going to post some examples, or, well, pages with examples of doing more integrals involving trig functions this week. I may not post them today. I'll get them up by the end of the week, but that way you have some more reference material for doing this stuff. These are rather complicated problems. As I said, this is one of the trickiest things that we're going to do this whole semester. So make sure to let me know if you run into any questions or have any trouble with any of the examples, and I'll be happy to try to help walk you through those things. But in the meantime, we've now dealt with the sines and cosines case. Next time we will start talking about tangents and secants. And you can kind of see where we're going. It's going to be a similar kind of thing there. And we'll sort of, well, you'll see what happens, but very similar kinds of stuff will happen there.